During this video, you will learn about the different type of elicitation that can be performed in the classical model, that is, eliciting subjective probabilities. Eliciting probabilities means, in fact, eliciting distributions of discrete random variables. This is different from the standard setting of the classical model, where distributions of continuous random variables are elicited. Let's start with an example. We may ask ourselves, what is the probability it will rain tomorrow? Notice that we are interested now in assessing the probability that an event occurs rather than providing assessments for an uncertain quantity. By assessing this probability, we fit a Bernoulli distribution to the binary random variable, whose outcome reflects that it rains or it doesn't rain. We are therefore interested in eliciting distributions of discrete random variables. Although the methodology allows for the elicitation of any discrete random variable, we will limit our attention only to binary random variables. So the questions will only address the probability of occurrence of certain events. Similar to the standard approach in the classical model, the aim is to evaluate experts' performance. This can be done by using the so-called calibration or seed questions. In this setting, the calibration questions will concern events that are known to have occurred or not, that is, by the analyst, and hopefully not by the experts. Or events for which it will be known if they occur or not, shortly after the elicitation. For example, asking now about the probability that it would rain tomorrow, or the day after tomorrow, or in 3 days, are calibration questions whose answers will be known in 4 days. The answer is whether each day it has rained or not. And the answers will be compared with the expert's probability assessments. The evaluation of expert performance will make use of the calibration score, or statistical accuracy, and the information score, just like in the standard classical model. However, the two scores are somewhat different than the scores you have seen so far in the MOOC. In this video, we will focus only on the calibration score and defer the information score to a later video. So, experts are asked to provide their subjective probability of events occurrence. These probabilities are assigned to probability beans. That is B1, which is from 0 to 0.1, B2 from 0.1 to 0.2, and so on, up to B10, which is from 0.9 to 1. Say I assess the probability of raining tomorrow in Delft. Since we are now in the middle of a rainy period, I assess the probability to be 0.8, which means that I place the event in the 8th bin, B8. Assume now I will answer 20 questions about the probability of raining in Delft over the next 20 days. My subjective probability assessments will lead to the following bin distribution. For 3 random variables, I assess a very small probability, between 0 and 0.1, of raining. For 1 variable, a probability between 0.1 and 0.2, etc. I therefore have 20 random variables assigned to 10 probability bins. Now, for every bin, Bi is associated with a probability of occurrence Pi, for I from 1 up to 10. Any value in the interval associated with the bin can be chosen. We choose, though, the middle value. That is, B1 will be 0.05, the middle value of B1. B2 will be 0.15, and so on. B10 will be 0.95. We also consider an I, which is the number of events assigned to the bin Bi. In our example, N1 is 3, N2 is 1, N3 is 2, and NS4 is 0, as there is no event assigned to bin B4, and so on. In our example, we can wait 20 days and find out which events occurred and which have not occurred. So basically, in which of the 20 days it has rained or not. Assume now 11 out of 20 events have occurred, which is marked by the red dots. Both events in B10 have occurred, for example, and 2 out of 3 in B9 have also occurred. We can then compute the frequency of occurring events. That is, we consider in bin Bi the number of events which have occurred out of Ni, which is the number of all events in Bi. This defines Si. Therefore, S1 is 1 over 3, since 1 over the 3 events in B1 have actually occurred. S2 is 0, since the event in B2 has not occurred. And by convention, S4 is 0. Finally, S10 is 1. We now have the theoretical probabilities assigned to each bin on one hand, and the frequencies of occurring events on the other hand. I hope this rings a bell, and you can see where I'm heading, similar to the standard classical model setting. That is, we will now measure the difference between the two probability vectors given by Pi and Si, which is given by the relative information I of Si and Pi, given by Si times logarithm of Si over Pi plus 1 minus Si times logarithm of 1 minus Si divided by 1 minus Pi. Given the two probabilities of occurrence, Pi and Si, we may ask now, how surprised would one be if one initially believed the probability to be Pi and learned afterwards it was in fact Si? We can now define the calibration score in the following way. Under the null hypothesis that Si is Pi, then the sum over I of 2Ni times the relative information of the Si and Pi is asymptotically chi-square distributed with b degrees of freedom. If we let f be the cumulative distribution function of the sum over 2I and i's relative information of Si and Pi under the null hypothesis, then we define the calibration score as 1 minus f evaluated as the sum over 2Ni relative information of Si and Pi. When sufficiently many variables are used, we can use the chi-square distribution. A rule of thumb implies that this approximation holds if and only if n times Pi is greater or equal than 4, or n times 1 minus Pi is greater or equal than 4 for all I. Simple examples can quickly reveal that Ni, and therefore the number of all variables, needs to be quite big. Recent developments propose a statistical hypothesis test that tests statistic has an exact rather than an asymptotic distribution. It is based on the observation that under the null hypothesis, Si times Ni follows a binomial distribution with parameters Ni and Pi. This leads to an exact null distribution, which is discrete and non-symmetric, especially for small n. We employ a two-sided p-value, which accounts for the fact that the distribution is discrete and not symmetric. That is, the two-sided mid-p value. You can find out more information about it, as well as simulations from a real study, in our recent paper. If you want to know more about eliciting probabilities in the classical model, then the first two references are almost the only available literature. Thank you for your attention.